So we're going to move into section 6.3, which is going to talk about volumes by shells. So this is a different way to calculate the volume of a solid revolution. And, you know, it's got its advantages. It's good in certain circumstances and not so good in other ones. So let's first understand how you calculate a volume by shells. Now, in this case, what we're going to do is we're going to rotate a figure around the y-axis. And instead of taking a slice perpendicular to your axis of rotation, we're going to take a slice parallel to your axis of rotation. So take a little slice in here, like this. Notice that that's different than the disc and washer method. How come it's different than the disc and washer method? Well, you're rotating around the y-axis. If you're doing the disc or washer method for a problem like this, in which direction would you take your slice? Be a dy slice, right? It has to be perpendicular to axis of rotation. So when I first look at your problem, I can tell if you're doing the shell or washer method just by the slice you're taking. Is it parallel to the axis of rotation, or is it perpendicular to the axis of rotation? So, okay, that's cool. Now, let's think about what happens when we rotate that around the y-axis. What's going to happen to that figure? Can you use your mind's eye to sweep that around? If you did, what you would get looks something like this down here. I apologize, I'm not completely coordinated with my little viz cam here. But what you get is kind of like a shell. That's what you're going to get. And you can see the cross section of that shell and imagine it rotating around, and you sweep out a volume. And what we're going to do, just like we did with our disc and washer methods, we're going to try and find the volume of that one shell. So, yay. Now, at great expense, I've procured this, now, I don't want to be crude, but I call them beer condoms, but, you know, a little beer holder, cooler, etc. And let's use this to try and figure out the volume of one shell. So I'm going to rip out the bottom here. There's no bottom in this. And the trick in finding the volume of one shell is to cut it open along the seam. So let's just cut this along the seam. There we go. And now what we're going to do, instead of trying to find the volume of a shell like that, let's lay it out flat. Now, essentially what I got is what? I've got kind of a really thin box, right? How do you find the volume of a box? I mean, that's an easier figure to deal with than a shell. So let's figure out the volume of a box. How do you find the volume of a box? Anyone know? No one knows how to find the formula of
times width times height.
Yeah, thanks, Mike. Base times width times height. Cool, the volume of one box. So that's what we need to figure out, is the base times width times height. Now, can anyone suggest what you think that width is going to be here? What do you think that's going to be in terms of our picture?
Is it dx?
It's going to be a dx, yeah. So we got one of them. We got to figure out the other two dimensions. But let me get back to writing some notes here. So the volume by shell, first and most important thing that you got to keep in mind is we've got to take a slice parallel to your axis of rotation. If you start out your volumes by shell by taking something perpendicular to axis of rotation, I'll probably just mark it wrong right there. I'm done, all right? Creating this stuff online is really difficult, so you're kind of making it easy for me if you do that. Take a slice parallel to the axis of rotation. So that's going to be a big difference between this and the disc and washer method, is the direction you take your slice. And that tells me, do you understand what's going on? Are you taking the slice in the right direction? So once we do that, then we're going to figure out the volume of one box. So let's work with a particular function. That was going to be y equals 2x squared. And I've got that graph over here, I think. How about here? There you go. Y equals 2x squared. And we're going to graph that and figure out its volume of rotation by rotating it around the y-axis. So here's a look at our problem. We've got that figure. We're going to rotate around the y-axis. Let me kind of sketch one in here for us. And let's fill this in a little bit. So that's x equals 2. This is y equals 2x squared. Of course, y equals 0 is your x-axis. So a parallel slice is going to be a dx slice. I think it was Mike that told us how to find the volume of one box, which was length times height times the width. And the width here is just going to be dx. And the height is going to be top minus bottom. And that better be in terms of x because we got a dx thickness. The top would be 2x squared minus the bottom, which is 0. So the hard thing left to figure out is the length. So I've got the height. That's the difference between the top and the bottom. So top up here minus the bottom. I've got the thickness, which was my dx. What I next need to figure out is the length. So how long is this? Well, that's just the circumference of a circle. That's all that is. So how do you find the circumference of a circle? Any circle, not just this circle.
2 pi r.
2 pi r. So 2 pi r. Now here's the tough part. The radius, that distance, well, this is just some general point, so that radius is just x. So this will equal 2 pi times x. Okay, that's fine. Let's put all these things together into this formula and find the volume of one shell. That is one of these, one little beer holder. All right, so volume of one shell, it's going to be volume equals the length, which is 2 pi x, times the height, which is 2x squared, times the thickness, which is dx. So overall, 4 pi x cubed dx. Nice. Nice. Now that's the volume of one shell. We need to find the volume of all such shells, and actually find the volume of the solid of rotation, solid of revolution. So I have to integrate. Let's take the 4 pi out front, integral between 0 and what? Well, this slice can go anywhere up to 2 or down to 0. So 0 to 2. When I integrate, that's going to be 4 pi 0 to 2 of x to the 4th over 4. These 4's canceled. 2 to the 4th is going to be 16. (16 over 4 minus 0 gives you 16 pi. Nice. So that's it's our first example of a problem by a washer method. I mean a shell method. How's that one looking? All right. So a good question might be, well, what's wrong with what we've got currently? Well, what we got currently doesn't always work or work well or the way we'd like it to. So let me show you an example of that. Is there anything on this one before I leave shell, or this first example on shells? Is anyone still out there? Okay. So it's probably 8. Okay. Let's take a look at this function. Y equals 1 over x between x equal 1 and x equal 2, and the y-axis, so like that. And we're going to rotate it around the y-axis, that is the line x equals 0. So let me help you out with what that graph's going to look like. So the graph of 1 over x is really part of a hyperbola. Kind of been rotated a little bit. So we take a look at it maybe here on Desmos. Just check. Just want to double check that I hit the record button. Yes, I did. Okay, so let's shut those off real quick and type in y equals 1 over x. And I want to limit that for x between 1 and 2. And let's make that a 1. And this is a 2. Okay, so pretty undramatic looking. Let's try and clean that up a little bit. So the area underneath this curve is what I want to do. I want to rotate around the y-axis. And let's do that for y is greater than 0. You don't have to become an expert with decimals. Oops, greater than 0. There we go. So it's this area that I want to rotate around the y-axis. So while you copy that in your notes, I'll be doing the same thing, trying to copy that into my notes so that we can work with it. Is anyone out there taking Spanish? Has taken it, taking it?
Yeah.
Yeah. So I remember one time getting curious about the word integrand in Spanish. And I was hoping for something meaty, you know, some really cool term like Spanish for meatballs is albóndigas or train is ferrocarril. But integrand in Spanish is just integrando. It's like, okay, it was just such a disappointment. It's like such a weak one. What Spanish are you in? Which level?
500. I'm not sure if that.
Is it like 5th semester or you're going on discussing the culture?
In high school.
Oh, okay.
Right.
All right.
So yeah.
Good stuff. Well, knowing a foreign language is pretty fun. So, okay. So here's our function. Y equals 1 over x between 1 and 2. And we're going to rotate that around the y-axis, which of course is the line x equals 0. That's fine. Now I kind of hinted at something just a little bit ago, and that is, you know, you don't always want to do the disk or washer method. By the way, if I wanted to do a disk or washer method, what kind of a slice would I be taking?
DY.
Yeah, you'd be taking a dy slice. And there's nothing wrong with a dy slice necessarily, but if you look at the region, your dy slice would be different from one part of the region to another. So below this line here, below the line of y equals 1/2, you'd have a different region. You'd have to calculate this volume in 2 parts, an upper region and a lower region. And that'd be kind of a pain. It's like, really? So I got to do 2 calculations here? Ugh. So what if we did things with the shell method? So first things first, for the shell method, Hunter, what direction are we going to take our slice?
To the left.
Dx or dy?
Dy.
Well, if we're rotating around the y-axis, you want to take a slice parallel to the axis of rotation, which would make that a what? Would they be a dx slice or dy slice?
Dx.
Dx slice, good, thank you. So it'd be a dx slice here. So let's do that. Take a dx slice. And the nice thing is that I don't have to set up 2 different regions here. It's just the same dy slice no matter where I take it. So, all right, let's draw that in. So it's going to be your dx right there. And we're going to need a few things. Let's figure out the volume of one shell. Volume of one shell. Now remember, we're going to go back and kind of think of it as really not the volume of a shell, but the volume of a box. All right, a very thin box. So volume is going to be the length times the height times the width. The width I'm always going to reserve for dx or dy. So W is dx. The height, that's just going to be this dimension right here. That's going to be your top minus your bottom. So that's h. Top minus bottom. What expressions could I put in for that? Marissa?
Would that be 1 over x minus dx? I don't know.
Minus, what's,
Oh,
not dx, but what's the equation of this line? 0. Just 1 over x minus 0. You okay with that?
thank you.
Thank you. So that just turns into 1 over x. Now the part where we got to think about is, what's the length of that? Now the length comes from the circumference of a circle. So the length is going to be 2 pi r. R is just going to be the distance from our point to the axis of rotation. And since I'm doing this in general terms, that distance is just going to be an x. That's where you're at. 2 pi x. So I've got all the expressions I need here. I've got my dx, I've got my h, and I've got my L. So let's put all those expressions in to get the volume of one shell. So this is tricky stuff. So, if you want to get some more help on something, or maybe I've gone over something too quickly, let me know. I'd be glad to spend a little more time on it. So let's take a look here. The volume of one shell is going to be 2 pi x times the height, which is going to be 1 over x. Uh-oh. That's bizarre. 2 pi x, 1 over x, times dx. That's got me feeling a little anxious. 2 pi x, 1 over x dx. Okay. Well, let's keep going. So that's going to simplify, right, to just 2 pi dx. Wow, I'm just not liking that. Something doesn't feel right. Okay, well, let's keep going. The integral of 2 pi times dx. Where are we going to integrate from and to? Anyone?
Would that be 0 to 2?
Not quite 0 to 2. Where's the smallest?
Would it be 1 to 2?
There you go, 1 to 2. Do you see the 1? Because we can't stay in this region past 1. So past 1, you're no longer in that shaded region. So yeah, 1 to 2. So it's going to be 2 pi times x between 1 and 2 2 pi. Boy, that just, Well, I'm not comfortable with that, but I don't see any mistakes. Mimi, do you see any mistakes there?
Oh no.
No? I don't see anything wrong there either.
X, dx.
Okay, no, we'll go with it. That's our answer. All right. So I didn't, I guess what's bothering me is that these canceled out. I just really didn't like that. But I don't see anything wrong with what we did. I'm gonna look at this one again after class, maybe during the break. But I don't see anything wrong there. It just worked out nice and easy. Tell you what, I promise not to give you that one or one so easy on the test, okay? So don't worry. All right, I'm sure y'all muted, otherwise I hear huge guffaws of laughter. So that's okay. Let's try some more here. So let's take a look at y equals 3. That's the region of y equals 3. Y equals 1/2 x squared plus 1. And x equals 0, which of course is just the y-axis. And we're going to rotate that around the y-axis. Now on the test, it's quite likely I could ask you to do one like this and set it up in 2 different ways. Set it up by shells, set it up by washer, and then evaluate it whichever way you find most convenient. But right now, we're going to work with practicing the shell method. So we'll do it that way. So this graph, 1/2 x squared plus 1, is going to be the graph of a parabola with a y-intercept of 1. So something kind of like that. Really lazy, wide opening parabola with a y-intercept of 1 right there. And then y equals 3 up at the top. So the area between is what we want. And the area between is going to get rotated around the y-axis. Good enough. Like I said, we're going to rotate this around the y-axis. Nicole, if we're going to rotate around the y-axis and do this by shells, which direction am I going to take my slice?
Would it be dx?
Perfect, dx, because you want a slice that's perpendicular to your axis of rotation. So, I mean, parallel to your axis of rotation. So that would be this one right here. So that's your dy slice or dx slice. And that's going to lead to a shell. We're going to want to calculate the volume of that one shell. Volume of one shell. Volume is going to be the length times the width times the height. And I think Nicole already gave us that the width is going to be dx. How about the height? Height is going to be how tall your shell is So top minus bottom. Can someone give me an expression for that? Anu? Maybe you can help me out. What's top minus bottom going to be here, please? Okay, Tony, maybe you can help out.
3 minus 1/2 x squared plus 1.
Perfect. So it's going to be 3 minus 1/2 x squared plus 1. Now, if you distribute that, that's going to turn into 2 minus 1/2 x squared. Perfect. Thank you, Tony. Let's see. There's one last thing that I need to calculate, which would be the length of this. That's going to be really the circumference of that expression. So 2 pi times r. What do you suppose r is going to be in this case? Right minus left again. Just going to be an x. So I've got my...
In every example we've done, it's just become an x. So is that something, like when would that change?
Well, let's see what happens when we do a dy slice.
Okay.
So yeah, so the next one we'll do, we'll try and rotate around a horizontal axis. That way we do a dy slice. So it's a great question. But yeah, your dx ones are typically going to be that. Where it's going to be different than x is if you have something other than the y-axis for your axis of rotation. So if I had x minus x equals -3 here, then the radius would be x minus -3 or x plus 3 would be the radius. So it's a great question.
Oh, okay.
But see, that's why I want you to get in the habit of top minus bottom, right minus left, because it's not always going to be so simple. And if you're in the habit of understanding this mindset of this is how you find these things, then when you get a slightly more complicated example, it's not going to throw you off. So appreciate the question, and we'll make sure we do a couple. Okay, so I think I've got everything I need there. I've got length, I've got the height, and of course I got the width as well. So dx. Let's put those all together. So the volume of one shell is going to be 2 pi x times 2 minus 1/2 x squared times dx. So just for giggles, I'm going to distribute the 2 in here because I noticed that I'll get rid of that fraction there. I'll write it as pi. Let's also distribute the x times 2x minus x cubed dx. So I just distributed the 2 and the x into here. Just to have a little cleaner expression. Let's now find the volume of the entire solid of revolution. So if you rotate this around the y-axis, then we'll take the volume of one shell and add it up for all such possible shells. But here's the $100 question. I'm going to start at 0. But where do I end? Where's this point? Where do those two lines cross each other?
They cross at 2.
I think so. Yeah, I think x equal 2. Now there's a couple ways you can try and solve here. Let me ask you, if you needed to find that point, someone came up with it pretty quickly, but if you needed to find that point, are you gonna figure it out with pencil and paper? Are you gonna figure it out with your graphing calculator? Or are you gonna go to like something like Desmos? how are you going to do it? How would you like me to demonstrate finding that point?
You can set it equal to each other. So y
Okay.
equals 3 and 1x or 1/2 x squared plus 1.
Yeah. So if you want to find that point, and it doesn't hurt to demonstrate this by hand. So your point of intersection is going to be where 3 equals 1/2 x squared plus 1. Or
I have
2.
a question. Sorry.
Yes.
When you distributed the 2x, isn't that be 4x before the
Yeah.
volume?
It should be 4, yeah. 4x. Thank you. Yeah, thank you. All right, so that point of intersection, really there's 2 points of intersection. There's a plus and minus 2. Obviously we want the positive one because that's going to be in the first quadrant where our region is. So.
Can you do it on the Greenfield calculator real quick? Or decimals?
Sure. Which one would you like? Your call, Marissa.
Decimals.
Desmos. Are you a convert? Did I get you liking Desmos grudgingly? All right. She's pleading the fifth there. All right, so let's take a look here. The nice thing about Desmos is just how easy it is. If we type in, say, 0.5x squared plus 1, and then let's also type in y equals 3. That's a little bit higher than my graph. So you click and drag, and then it brings it into view. And then you come over here and click, and there you go. There's your point, x equal 2. Now, when we solved it, we got both solutions, 2 and -2, but obviously we want 2 for our purposes. So, cool. Thanks, Marissa. All right. So that should be a 4, right? Yeah. All right, so let's make that a 4. And this one a 4. But the big point here is that the limits go between 0 and 2. And you're going to have to find those. Maybe in one of the subsequent problems, we'll show you how to do it on a graphing calculator. Now, let's find an antiderivative. That's going to be 2x squared minus x to the 4th over 4. Plugging in a 2, I'll get 8 minus 16 over 4 is going to be 4. At 0, they're both 0, so I'll end up with 4 pi. Okay. Beautiful. I like that one. I like that one. It worked out nice. How's that one looking for you guys? Did that work out okay for you? All right. Let's take kind of an early break here. We'll come back and do some more.